I'm talking about using ocean circulation models related to bottom pressure records like many of the other speakers. This is, and I've been collaborating with Alex Kuropov on this, but Alex got to present his own results this time, so that was much better. And I'll be focusing on some slightly different things than previous physical oceanography speakers, specifically about stuff that happens between the surface and the bottom. So as you know, there are lots of things that can influence bottom pressure, and we've seen amazing examples of these in the talks that came before me, which is pretty exciting for me to see this all come together. And in particular, I'm focusing on the parts associated with non-tidal sea surface height variability and the internal density structure. And you saw that these can be influenced by like coastal trapped waves. Alex didn't talk about things like the California undercurrent, but did talk about El Nino. And then I'll be focusing more on eddies, which have come up as like instabilities or intrinsic variability in some previous talks. Just like Alex, we think of pressure, the hydrostatic pressure, as affected by sea surface height and the density structure. So that G rho prime is the variation associated with the density structure. And I'm glossing over all that amazing, interesting stuff associated with the inverted barometer and atmospheric pressure. I'm just ignoring it, really. Now, I'll be using model output for this and analyzing actually the same current meter locations that Alex showed in his talk, but I'll be using a much higher resolution numerical model. You can see underneath this is Alex's WCOFS model, the one with all the color on it. And then I'm using a much smaller regional model called Live Ocean. And one thing about this is it has much higher resolution than any of the models you've seen previously. Most of the results you saw from like HICOM and Glories and Echo 2 are kind of 10-kilometer grids. Alex is much smaller, 2 kilometers, and then mine is more like a 500-meter grid on the shelf and slope. So resolves more bathymetry, so on, but because it's built to also work on estuaries and internal tides and things like that. So these are the mooring locations. The same ones Alex showed, 2 on the shelf, 1 on the slope, and then I'll focus on 1 in the abyssal ocean, about 2,500 meters of water. So, or almost 3,000 meters of water, sorry. So, oh, and the title of this is wrong. It's not CEO4, it should be PN01A. Anyway, there's a time series here. The x-axis is time over the course of a year, and this is from a mooring extraction in the model. And then the y-axis in the top 2 panels is depth. And in the upper one, I've contoured the low-pass baroclinic pressure anomaly. So what I'm calling baroclinic pressure is just the part of the pressure anomaly associated with the density structure. And then the low pass means I've filtered out tides. And then the fact that it's an anomaly means I've removed the annual average at all depths. So all you see is the deviation from that. And you see that it's something that starts out near 0 at the surface because it has to by construction. And then over the thermocline, it gains some signal. And then some places has more structure, like here you see there's a subsurface eddy of some sort, but changes sign a lot. If I add to that the part due to the sea surface height anomaly, you see this middle panel, and it gets a little more high frequency variability, probably due to coastal trapped waves, and often changes sign. So that's interesting. And then the bottom, just like in Alex's plots, split just looks at the bottom pressure associated with the gold colored line is the part due to sea surface height. The blue line is due to the density structure. The red is the full bottom pressure. And you see this thing that Alex and previous people had mentioned about compensation. That is, like here, the sea surface height is high, but it's essentially the sea surface height is pushed up, but the density structure below it is pushed down, and the residual is somewhere in between them and a much smaller signal. Alex showed a nice example of how this is associated intrinsically with wind-driven upwelling and downwelling on the coast. They tend to have high sea surface height with depressed isopycnals. Ken showed sort of a similar structure for coastal trapped waves. That is, they have that zero node line as you get to deeper down. And it's also a consequence of what we call a quasi-geostrophic spin down or bottom friction. And I'll show a diagram of that. And in particular, just focusing on this part at the end of the year, you can see that at this location, there was an anticyclone parked over the mooring location, causing this several-month signal. Here's a picture of the model at 300 meters depth, and we're left panel is salinity at 300 meters, right panel, the color is temperature at 300 meters, and then there's velocity vectors as well. And you see there's a field of eddies, and that's the type of things that Chris Hughes was talking about and as being the intrinsic variability. And you can see pretty rich eddy field. This anticyclone is this red patch sitting over the deeper mooring here. And I'll show a movie of that in a sec. Just the world's shortest lecture on quasi-geostrophic spin down, baroclinic spin down. This is a sketch of an eddy. In this case, an anticyclone has high sea surface height. And then if it extends to the bottom friction, the bottom Ekman transport tends to go out away from it. Then what we call Ekman pumping at the top of the bottom boundary layer is pulling down. And the consequence is that it pulls down the density structure. And it leads to there being weaker and eventually zero currents as you get close to the bottom. So that's physically one reason why we expect compensation is because friction removes energy from the bottom and leaves you with this compensated density pressure structure above it. This happens over a time related to H over delta 1 over F, which is H is something like the water thickness, delta is the boundary layer thickness, and 1 over F is just like a day. So, okay. And finally, one weird thing I was forced to think about in doing this is models like mine and Alex's, they get their open boundary conditions from HICOM. HICOM assimilates information from Argo buoys to keep adjusting itself. And so it does adjust itself, but it also changes from one version to the next. So here's just some records of, many year records of salinity and temperature at 2000 meters from the HICOM model, and the colors is different versions of the model that just came online at different times. So a lot of weird stuff happening, scary. And finally, I don't think I really need to go over these very much. They're just what I said during the talk. And then last, just for fun, here's like the eddy field at 300 meters for a full year, just to give you a visual sense of what this intrinsic variability looks like. And these are just daily snapshots, but at this depth, they mostly represent the geostrophic currents. You can see eddies. One thing of particular importance is that the offshore eddies tend to be bigger. Those are like mesoscale eddies, but at the coast or the shelf, this line here is like the shelf break. They're more generated by flow topography interactions and tend to be smaller scales. And that's the kind of things you're seeing now.